So today what I am doing is just sorry, to know little bit of FVM and then compare all the three, that what is the difference between them, so that we can appreciate that what are the advantages and disadvantages of each one of them. Okay, so what is happening in FEM method is, we now in FEM method what we do, that it is just like suppose you have this domain, right, and you can have unstructured grid here, like just like in FVM we have unstructured grid here, and we can divide it into number of elements like this. And these elements can be of any shape. So you will get all the advantages of unstructured grids. Okay. Now, how does it different from the FVM? We take an element here. Let us take this element here. Now, there are something called, okay, these are the nodes. Okay. So we know values at these points. So you have U1 here, U2 here, and U3 here. Okay. These values are known in the sense that we are focusing on them. These are our, basically they are unknowns, but we are calculating values at this point only. So if you talk about FVM, so this is FEM, let us say FEM. If the same thing happens in FVM, what we will do, this is the same element, okay, and we are talking, when we are talking about FVM, then we will find value at this point, centroid, and also we will find values at these points, and we have to calculate flux at these points. Are you getting the thing? That we are applying conservation equation. So conservation equation, the terms will come accumulation, advection, diffusion, and storage or source. All these things will be calculated considering this as a volume. Okay. Now when we have to find flux, we have to find how much is flowing out from here, and here. So suppose we are talking in terms of energy. So how much energy is flowing from each phase, or it is entering in. Okay. It can be through advection or through diffusion. But whatever is entering inside the volume will be entering through the surfaces, boundary surfaces. So whatever will happen here is we are entering from, so these are the boundary surfaces. So what we do, we calculate flux at boundaries. Right? Accumulation is within volume, generation is also within volume, and we balance it out. When we are talking about FEM, then what we do, we are not calculating the flux. What we are doing, we are talking about these values, and everywhere else in this domain, in this element, values are found in terms of shape function. So there is something called shape function. So if you want to find value at any point here, it will be a function of u1, u2, u3. So in a way, if you know u1, u2 and u3, you know every value within the domain, within the element. Okay, so this is the technique basically used. Now this is further used. These intricacies will become still more difficult if we go into that. So I am just telling you that in this case, a technique is such that you are finding values everywhere in the cell on the basis of the nodes. Okay, where there were centroids and phase center, here there are nodes. Okay, and the values are found at all the points using shape function, and these shape functions are decided by the user. Okay, so as a result, that would lead to then different formulation comes up and we solve it. Okay, so how do we do that? That is still a complex matter. We'll not be discussing that because that will become too much for this course. So this is what is happening, and the same thing I can show you here, that this is the thing. How does it look like? That what are these shape functions? So we are considering so this is the linear element here. Okay, and what we do, this is a triangular element, linear triangular element. So there is a these are the functions, these are shape functions. Okay, this is shape function, right? And if you just see that, you can find the value. Suppose you want to find value at point xi. Okay, if you want to find value at this point, the value of xi is 0 and value of eta is 0. So when xi is equal to 0, and when eta is equal to 0, this point becomes your 1. You can say this is your A point, right? Similarly, when xi is equal to 1, eta is equal to 0, it becomes B point. This is beta. And similarly, you have xi is equal to 0, eta is equal to 1, this becomes C point. Okay. Now, if you want to find out value of u, if you want to find out value at xi n, right, it is found out like this: u1 into 1 minus xi minus n plus u2 into xi plus u3 into eta. Now you put value of xi and n here. If suppose xi and n are equal to 0, so u0 comma 0, that will become u1, right? And if you want to find out u1 comma 0, that will become u2. This is your u2, and this point is u3. And if you put u, calculate at 0 comma 1, this will become u3. Okay. Now in between you have, so these were the 3 points we talked about, but in between also you have value for xi and n. So all these points can be traced with the help of xi, because xi is equal to 1 is this point, n is equal to 1 is this point, and xi is equal to 0 and 1, and eta is equal to 1, 0 are this point. So all these points can be written in terms of xi and n. As a result, the values at each point can be found out from this equation. Right? And this is one of the simplest example. This is one of the shape function. These are the shape functions, and you have used that to find out the values. So the thing is, in FEM, what we are doing is, we are taking an element, and everywhere in the element we can find the value based on some shape function, and then we use it. Okay. So in a way, we don't know that how the element is behaving. The simplest one is that you take average of all of them. So this is what the cases we took: linear addition of all the points. That means effect will be linear. It could be other function also. So this is how it does. From here on we proceed, and this technique is primarily used in stress analysis, solid mechanics. But this is applicable in CFD also. Okay. So this is okay. So these are the shape function. You can see that this is what we are doing it. Writing here. And you'll find U00 is U1, U10 is U2, U01 is U3, and you can find out what will be the point. That is, xi is also half, n is also half. It will be somewhere in between, in the center. Okay, and you can find these values. Now these linear shape functions are simple examples, and more complex shape functions are used for higher order elements. You can use higher order. The choice of shape function depends on the type and order of finite element used in mesh and desired level of accuracy. So the shape function will determine what is the level of accuracy. And just to mention again that this is primarily used in stress and strain analysis. Okay. So we will close it here. Now what I am trying to do is just compare the two as much as we can understand the difference between the basic. So now we are talking about all the three methods together. So what is FDM? In FDM, discretization of partial differential equation is called finite difference. Okay, so that is called finite difference equation. Okay, discretization of integral form is called finite volume method. So this is the one basic difference. In one case we are discretizing the integral form, in other case we are discretizing the partial differential equation. Okay. In finite difference, dependent variable values are stored at nodes only. So nodes, you understand, if you have this, these are the nodes, and this is the centroid. Okay. Now finite element method, the dependence value are stored at element nodes. So when we talk about finite element method, again the values are stored at the nodes only. This is what I just told you. These are some links, you can read more about them. Okay, and mostly I will be covering whatever is there. I will be covering here. These are just for reference if you want to. Now finite volume method. In finite volume method, the conservation of mass, momentum and energy is ensured at each cell finite volume level. This is not true in FDM and FVM. This is the basic difference. The conservation of the quantity that equation is not applicable at element level in FEM and in FDM also. But in finite volume method, it is applicable at the element level. It's always better to use governing equation in conservative form with FVM to solve any problem, which ensure that the conservation of all the properties in each cell control. So we begin with governing equation, which is conservation equation. So we, for all the cells, all the quantities are conserved, and which is the natural process. I look at it in a slightly this way, that our physics is being ensured at each cell. Instead of physics being ensured at the whole domain level, physics is being ensured, is validated or applied at the cell level, which makes the solution much more accurate. Okay. Again, in finite volume method, dependent volumes are stored at the center of the finite volume. So this is what we are talking about. These are the, so we are only storing these values at this point. If there is a second element, we are storing here. If there is a third element here, we are storing here. At the nodes, we do not store. At these are our nodes. So we are not storing values here, only at the centroid. Okay. Now we talk about comparison between all the three. Again, to highlight this, same thing, almost I have covered all the points, but just to, because I have developed this topic in stages. So wherever I have written, I have just put them separately in separate paragraphs, and there is a lot of repetition. We can combine all of them, but at the moment they are in different stages. We have done it. So let's see all of them. Finite difference method, discretization is based upon the differential equation to form the of the PDE to be solved. This is, we have been, each derivative is replaced with an approximate difference equation formula that can generally be derived from a Taylor series. So FDM we are using Taylor series, and the equations PDE is being converted to finite difference equation. This is what happens. Partial differential equation gets converted to finite difference equation. This is what happens in FDM. And we use Taylor series for that. Okay. The computational domain is usually divided into hexaedral cells, the grid, and the solution will be obtained at the each nodal. Again, we are saying same thing at the nodal point. FDM techniques are good for structured grids. Okay, so generally they are applied for structured grids, and each nodal point becomes the point where the value is stored. FDM is easiest to understand when the physical grid is Cartesian. When that means x, y, z, all the three are mutually perpendicular. But through a use of curvilinear transforms. Now there is a technique in mathematics where you can convert the coordinates from straight coordinates to curvilinear coordinates. And even in curvilinear coordinates, you have orthogonal curvilinear coordinates and non-orthogonal curvilinear coordinates. Okay, curvilinear coordinates are of two types. One is orthogonal and the second is non-orthogonal. Now, what is an orthogonal curvilinear coordinates is that at all points the coordinate system is perpendicular to each other. Okay, but coordinate itself is changing. So if you look at this diagram, this is a curvilinear coordinates, orthogonal curvilinear coordinates. Now you see the actual domain is like this, and this is the thing. So you are dividing along the curves. Okay. Now if you look at any point here, the coordinates are perpendicular to each other, right? And what you are doing is, this effect of curve is actually transferred to your equation. But what is the advantage? That here you can solve this type of domain without resorting to volume method, unstructured grids. You can create structured grids like this, right? Another example is this. Now you see, this is the domain. Domain is something like this. I am not covering all the lines. You can see this is our domain. You can, and we have filled it with logical rectangles. This is a logical. We have converted the domain into logical rectangle. 4 sides are there which are defining the. So you have one side this, one side this, one side this, and one side this. These are the 4 sides. None of them is straight. So that is why we call it a logical rectangle. Okay? Logical rectangle, or quadrilateral you can say. In reality, this is not quadrilateral. Oh, sorry, it's not a rectangle. And this type of coordinates can be used. And now the advantage is that it's a structure grid. Each point is defined with respect to the other. Okay, so you can build in whatever the difference is coming because of the curves, that is built into the equation. So equations become much more complicated. They're not those simple, right? And you can do it. Okay. The discretization results in a system of equations of the variables at nodal points. So this we are talking about FDM. In FDM, what will happen? Our equations are developed at nodal points. Okay. And once solution is found, we have a discrete representation of the solution. So what happens? Finally, we have a domain, and at different points, we know the values, and we can extrapolate to find the whole domain, fill the whole. This is what CFD happens. Initially in CFD software, what happens? It finds values at fixed points, or even at moving points. Finally, when you have the solution, you have only a solution at a finite number of points in a domain. All the adjacent region is extrapolated and filled with colors. So you think that you are getting a uniform, you have found solution at all points. No. Even when you ask, suppose your grid is like this, cell is like this, you have found the values at these points. If you want to find some value at some middle point, the software will actually calculate the average and give you. It will take the weight of all the 4 points which are around it, 3 points around it, and give the value. Okay? We are not getting values at all the points, and that is why it is called numerical technique. In none of them, whether it is FDM, FVM, or FEM, you are only getting values at certain fixed points. Okay. Now, when we talk about FVM, discretization is based on integral form. We have again talked about it. I am saying there is a lot of repetition here because I am yet to formalize into a combined, because I am reading from different sources and I have put them in the same file. It will take some time before I actually combine all of them. So it's an integral form discretization is being done. The partial differential equation to be solved is conservation of mass, momentum and energy. Okay. The computational domain is discretized into finite volumes, and then every cell the governing equations are solved. The resulting system of equations usually involves fluxes of the conserved variable. Thus calculation of flux is very important in FVM. So this thing we have talked about, where we talk in terms of conservation of a quantity, right? We have seen this diagram before. These are the fluxes. Fluxes means something flowing per unit area per unit time. So you multiply it by the area, you get the quantity which is flowing. So if there is a flux, you can say phi per unit area per unit time, delta phi. You can say phi which is flowing out. So you multiply by area, you get phi per unit time. You multiply by delta t, you get the total flux which has flown out, and it can be Q. So amount of heat flowing out per unit area per unit time. This is called flux. Okay, so this is what has to be calculated, and because flux are calculated at the surface, so what, even if you know the value at the center, you have to have the value of the parameters at the surface also. Again interpolations are done, and we'll talk about that in a little while. The basic advantage of this method over FDM is that it does not require structure grids, right? And the effort to convert the given mesh into numerically structured grid is not required. So trying to convert a domain into a structured grids sometimes become quite tedious. So that labor is saved. So we have talked about basic advantages. So that is one advantage, that you can take any shape easily. The second is conservation is at the smallest level. Okay. As with FDM, the resulting approximate solution is discrete. However, unlike FDM, the variables are typically placed at cell center rather than at nodal points. So in both the cases, your solutions are discrete, right? In one case, if your cell is like this, or in, let us say in FDM, your cell is like this, FDM, you know values at these points. If you want to find out here, you have to do the interpolation. In case of this FVM, what is happening is, you know value at this point, and if suppose you want to find out any value here or here or here or anywhere at this point, you have to interpolate. Okay, so both the techniques are giving you discrete values. Remaining portion is being done by interpolation. Okay, this is the diagram we have. Now, when we talk about FVM, these are the centroids, right? And these are the phase centers. So these green dots telling you phase center. So what will happen? You are knowing values at the centroids only, and here you find value by interpolation. And you can use this value to find the flux. Okay, so this is what we do. And if the grid is of rectangular, again in FDM, your values are known only at this point, while in FVM, your values are known at these points, green points. These are the centroids, and blue, which is also centroid of the main, and these red are basically phase centers. Through interpolation you find out. This is not always true, as there are also phase-centered finite volume methods. So people have also developed that, okay, instead of talking about centroids, we can talk in terms of phase center. So that is also possible. But it is discrete, because phase center is also one point on the face. Okay. In any case, the values of the field variables at non-storage location. So wherever you are not stored, e.g. vertices, are obtained using interpolation. That you have to do the interpolation. Now we talk about FEM again. Now FEM method is discretization is based upon a piecewise representation of a solution in terms of specified basic function, or the shape functions I have talked about. So unlike in FEM, you see what is the difference in the two. One is FVM and one is FEM. In FEM, you know values at all the points through a function which is arbitrary. So that doesn't mean these things are calculated. Only thing, you are able to scan the whole element using some function which you think is the right one. Okay. While in case of FVM, you only talk about centroid, right? And then there will be next centroid and there will be next centroid. So this is the difference. So you can say in FEM, finite element method, you have created a dummy, you can say, image of the element using some functions which you think will fit in there. It's not necessary those functions will fit in. Okay. The computational is divided into smaller domains, same. The solution in each element is constructed from the basic functions. Okay. Here in FEM, equations are obtained at nodal values that must be solved to. So you are developing equation at the nodal points. Okay. Now we say that FEM provides a continuous solution. Yes, to an extent. But that continuity is you can say subjective. You are putting a function there. FVM is generally expected to provide better conservation properties, but opinions vary on this point also. So I don't know about this, how much detail it is there. So now this is important. If you are trying to decide which method to use, then the best path is probably found by consulting the literature on the specific problem. So it's not that you have understood the fundamentals and you can solve the problem. You have to always refer to what people have done and adopted. You have to keep on referring. And the reason for that is that there are many assumptions in between. It's an approximate method. Had it been, you can say, perfect method, CFD, mathematically perfect. I'm not saying there is imperfection there, but there are a lot of approximations there. Had it been a perfect method that there is no approximation involved in it, then you can use the basic rules of mathematics and solve it, and you don't have to refer to other things. Because all the laws which you are following, they are there. they are valid. But here what is happening is that you are going partly logical, partly based on experience. You are doing approximations. So at each level you have to refer to the people who have traveled on that path, that how do they suggest what is good, so as to reduce your labor. So, and this is the point which makes CFD your asset, right? It's a weakness also, it's a strength also, because if you follow CFD, with every year you have put into CFD work, you become richer, your value becomes bigger, increases, because experience का value है. If you are only following the formula, okay, and somebody understands that formula, then there is no need of you. This is how it happens in the industry. This is how it happens. Experience is useful for certain time, so long, because experience, otherwise other person, if he wants to exceed you in experience, he has to spend so many years also. So you have that lead, you have started earlier, you always are the leader. But in case of those approaches which are purely scientific, there is no experience required. Once you understand the laws of it, and then somebody, once he understands it, he is equivalent to you, right? Then he can surpass you also. So CFD is such a knowledge which will keep you always in demand, although it is complex, but that is the beauty of it. Are you getting the point? Again, there is certain things. Let me see, rush up through this. If some important points come up, this is I have taken from ChatGPT, because I tried from other sources also, I was not getting good answer, but here I got some reasonable answers I can share with you. When you talk about grid structures, we have already talked about grid structure, that in FDM grids can be both structured and unstructured, but regular Cartesian grids are common. FDM is not a technique where you cannot go for unstructured grids, right? But Cartesian coordinates are always better, structured grids are always better. But in FVM, you have irregular shape size, we already know that we can have any type of unstructured grids, means you can have any shape you want. Node placement, we have already talked about this. One is in both FDM, it is at the nodes. In FEM also it is at the nodes. Nodes are placed at the vertices of the elements, right? So in both the cases, values which are stored in the computer, they are at the nodes. Okay. Flexibility of mesh, we have seen it, that typically FDM uses a fixed grid structure, and modifying the grid can be challenging, especially in complex geometries, right? FEM provides more flexibility in handling the complex geometries. Here we talk about fixed structure, okay? Accuracy and convergence. FDM may require a finer grid to achieve the same level of accuracy as FEM. Now you see, what is the advantage FEM is giving? Because FEM is interpolating. You can have a, you can say, wider grid. The FDM requires a finer grid to achieve the same level of accuracy as FEM, especially in regions with complex geometry. FEM often allows for better accuracy with relatively coarser mesh due to its ability to capture local behavior through element wise refinement. So the local behavior is taken care of, right? So this is the advantage, and this advantage becomes quite more important in case of solid mechanics, where the behavior of the element, because in CFD what is happening, it is all gas, fluid or liquid, and fluid and liquid are thus they are more uniform because they are free to move. No? What is fluid? Molecules are free to move. So they tend to form a uniform, or at least in a region it is more uniform. Whatever the flow is, it is uniform at a local level. But in solid mechanics, that doesn't happen. The elements remain where they are, they cannot move, they deform, but the material cannot leave from there. As a result, behavior of the material at that particular element becomes important, and even in the direction. So these functions, shape functions, become important. Lengthwise, how the element is behaving, widthwise, how the element is behaving, those things come into it, and that is why because these things actually not happen much in case of CFD. And I can't conceive a thing where the element you require, except for averaging, you require anything else for a finite volume method, right? Boundary conditions. Now in FDM, you have to, boundary conditions are applied at grid points because you are not talking about in between. But in FEM, boundary conditions are applied to nodes along the element boundaries. You can also apply, suppose this is your boundary. So you can also apply your boundary condition here. So it becomes a step better, right? Even when you take an average function, suppose your fluid is like what? Uniform fluid, let us say. So your shape functions become linear, just a weighting, you can say addition, the one we discussed. Now you have the advantage, that additional advantage, that at this point you can define the boundary even at the face, where in case of FDM you have to define only at nodes. Okay. Equation solving. FDM, it directly discretizes the differential equation resulting in algebraic equations that are solved. So solution is slightly tricky in FEM. In FEM, in FDM, so what happens, you have algebraic equation at all the points, solve them together. But in FEM, what it involves, conversion of differential equation into variational form. So this is some other technique is there which we have not discussed, which is then discretized, resulting in system of equation often solved over elements. So something like variational mechanics is being used there, and it becomes a different type of approach. Application range, regular geometries के साथ, simple boundary condition. FEM can be used with irregular geometries, complex material properties, and varying boundary. Right? In summary, both FD and FEM are numerical methods for solving partial differential equations. They differ in their approach to meshing, interpolation, and handling of complex geometries. Right? The choice between them depends on the specific characteristics of the problem at hand and desired trade-offs between accuracy and computational efficiency. So you are always thinking in terms of what is your accuracy of the solution and how much time it will take on the computer. Okay. So this is how you have to decide. Now another 10 minutes we will this is also from chat GPT. What is the difference between FEM and FEM? So it becomes clear to us that what these techniques are. Okay, again, as far as control volume concerned, it's a finite volume method, and FEM focuses on conservation of mass, momentum and energy within each control volume, right? And this is not with FEM, right? FEM involves dividing the domain into smaller interconnected elements. Same thing up to this point. These elements are typically triangle or quadrilateral in 2D and tetrahedral or hexahedral in 3D. Is stopping all the shape of. Normally, both in FEM and FEM, your 2D you have triangle or rectangle, and 3D you have tetrahedron or hexahedron. This type of break is there. The solution is approximated within each element using interpolation function. This is the only difference. FEM is not talking about within the element. You can say that. And FEM is talking also within the element. This is the only difference between. And of course, their equations will slightly become different, their solution technique will also become different. But as far as we are concerned, in FEM, he is talking about within the element also. And in FEM, because we are not talking about within the element, it becomes average. Okay. Variable of interest, now you see that FEM allows for the solution of a broader range of problems, including the problems involving stress analysis and structural mechanics. So FEM is more useful. The special benefit of FEM is this: stress analysis and structural mechanics. So if you meet the people who are doing structure mechanics, they will always talk about FEM. Their FEM is default technique, in CFD FVM is default technique. Okay. Discretization, now in FEM we already know that what we are doing in FEM. In FEM the problem is then discretized by approximating the solution within each element using shape function. Same thing is mentioned. Mesh types are both same, no problem. Boundary conditions, yes. In FEM, boundary conditions are typically applied at control volume faces. Okay, and in FEM the boundary conditions are applied at the nodes of the element. Okay, of course you can give shape function at the face also. So the difference would be that here you will have a single value for a face, because when you are talking about a supposed element and you want to put boundary condition on this, and if you are talking about this face center, so that value is same for all full. But in case of this is FVM, in case of FEM, when we are talking about FEM, you give value at this point, you give value, and you can give value at this point also, because you have shape functions. So that you can define. Consistency with conservation laws. FEM is inherently satisfy conservation laws. That is one of the best, the major advantage of this. Requires careful formulation and handling to ensure conservation properties. इसमें conservation properties को you are foregoing. Okay. In summary, both FVM and FEM are powerful numerical methods for solving PDEs in CFD. The choice between them depends upon the specific problem, geometry, and nature of the variable involved. FEM is often preferred for problems involving conservation of laws, while FEM provides more flexibility for a broader range of application, including structural mechanics. Okay. So this is all about these different techniques, and we will close here for today, and let me tell you about what we will be following after this. Okay, so in the next lectures we'll be talking about how to apply FVM on a problem. Okay, we'll take a simplest problem, simplest formulation, and we will get the equations. Okay, and we'll do it with FDM also. Okay, once we have got the equations, so what now we are showing is basically how we can get equations which are finally to be solved. So FDM equations will be on the points, node points, and FVM will be based on the elements. And finally we will get algebraic equation in both the cases. Okay. Then we will, once we know how to solve those equations, create those equations, then is left is how to solve them. Okay, and there we talk about mathematical techniques.